Okay, so here's the last problem, problem 3 in homework 16. It's been a long journey. Let's do it together. Here we have this 4-bar linkage with the dimensions of 8 inches, 24 inches, and 20 inches. This is arranged at 60 degrees and 15 degrees at this instant, and it is rotating counterclockwise at 10 radians per second. And it's increasing at 5 radians per second squared. And we want to find the angular velocity of link, we call this rocker, it's a rocker link, CD. So let's get to it. Oh, must have messed that up. Okay, so here it is written out. And, okay, so I'm going to start with this link right here. And maybe, so I'll write this link AB. It's a good place to start as any. Could have left myself a little bit more room, but I'll deal. So we're going to have a velocity coming right here, velocity of B, given that omega AB is going in that direction. So we'll find the velocity of B is omega AB LAB, or 10 times 8 inches, so 80 inches per second. And let's take a look right there. That's going to be our 30 degrees. While we're here, let's do the acceleration analysis here. And so we're going to have an acceleration of B with respect to A in the normal direction. And by the way, that's going to be 30 degrees right there as well. And I might as well go ahead and guess that my alpha AB is my guess. Whoop, spelled guess with, there's a U in there for some reason. Nobody knows why, right? There's a guess. And so that's going to make an acceleration right there. And I could cram this in, acceleration of B with respect to A in the tangential direction. That's what that arrow is representing. Let's try to free this up and make it look a little neater here. Should have moved the thing down, used more paper. I know. I tell people that all the time, and I don't listen to my own advice. Okay, so we have the acceleration of B with respect to A in the normal direction. That's omega AB squared LAB. So that's going to be 10 squared times 8. And so we're left with 800 inches per second squared. And the acceleration of B with respect to A in the tangential direction. So we have, you know, I just wrote guess. It's not a guess. We know that direction. We were given it. What was I thinking? I don't know. So what was that? They told us it was 5. 8. Could do that. 40. Inches per second squared. Now, it's going to be in our best interest to turn this into X and Y, I think. Just make it life a little easier. So we'll say the acceleration of B in the X direction is equal to, all right, so which one did I start with? I just started to go with the tangential first. So we say that's negative 40 times the cosine of 30, and then it's also going negative here for this one, negative 800 times the sine of 30. So I got negative 434.6 inches per second squared. And then the acceleration of B in the y direction. By the way, we could have done that with a coordinate transformation, but we already kind of have. We could just look at the angles too. It's the same thing. All right, so this one's in positive direction. This one being the tangential one. But we still have a negative y direction for the normal. I could have squeezed it right there side, but I'll put underneath it. So this ends up being also being negative 672.8 inches per second squared. Just remember though, I'm going to probably draw it in the positive direction and then stick a negative number in there. I just don't want to double dip with the negative into the negative. So that's for later, but now let's go for the ICR of link BC. And when we do the ICR of those, remember that we can like just draw and extend these lines, and we could figure out where these are going to go. So we kind of have sort of a guess already about what the thing is going to look like. I don't want to make it too big so that it will extend all the way down. So, and something like that right there, right? So this velocity is coming upwards like that right there. That's our VB that we got up above, right? And so let's take a look. Okay, so a couple things that we know. We know that right there is 15 degrees, right? And we know this right here is 60 degrees, right? Because that is 60 degrees, so that has to be 60 degrees. So we have that 75 degrees. That's cool. We also have that this is 15 degrees. Therefore, this is 75 degrees as well. Interesting, huh? So 75 and 75, and what we're left with is that this has got to be 30 degrees. So this right here is going to be my RC with respect to ICR, and this is RB with respect to ICR. And it's 75 and 75, so these two are equal to each other. This one has a length of 24 inches. So RB with respect to ICR divided by sine of 75 equals to 24 divided by the sine of 30. So we get RB with respect to ICR equal to 46.36 inches, which is also equal to the R of C with respect to ICR. And looking at this, we note that we get an omega BC going in that direction. We also note that we're going to have now horizontally VC is going to be in that direction. Come on, there you go, focus back. All right. So since we know that VB is equal to omega BC RB with respect to ICR, we can find omega BC is going to be equal to VB over RB with respect to ICR, which we just found this to be 80, so divided by 46.36, and we get an omega of, where did I just do that wrong? I think I think, yeah, okay, 1.7256, I guess. I decided to put another sig fig in there. And that's counterclockwise, we note. We could also say, by the way, that VC is equal to VB. So this is also going to be 80 inches per second, this VC, because that's equal to that. All right, so now we can continue on. And this is page 6. We'll finish all this other stuff up later. I'm going to go to the link CD. So this is going to be link CD. And it's just going to be a vertical link in pure rotation. And I already have the velocity here, VC. Therefore, omega CD is going to be in that direction. So writing that out right here, we see that VC is equal to omega CD times LCD. So omega CD is equal to VC over LCD, or 80 divided by 20. I could do that in my head. It's 4 radians per second, and that's counterclockwise, we know. And so while we're here, we can also get the acceleration of C with respect to D in the normal direction. And I will go ahead and guess alpha CD. Now this one is a guess, is in that direction. And we have the acceleration of C with respect to D in the tangential directions right there. So we can find out the acceleration of C with respect to D in the normal direction, which is, by the way, we know is the acceleration of C in the y direction, is going to be omega CD squared LCD, or 4 squared and 20. So that equals 320 inches per second squared. We also have the tangential one, which we happen to know is also the x direction, and that's alpha CD LCD, or alpha CD times 20, to be determined. Now we do acceleration analysis. Of link BC. All right, so I don't want to make this too small, don't want to make it too big. It's got to be like 15 degrees, something like that. They're going to be too close to each other. Shorten them up a little bit. Not satisfied. Not satisfied at all. Come on. Yeah, you're doing a great job on that one. Let's move this guy over there a little bit. All right. All right, so what do we know? Yeah, see. It's going to be important that we be able to like figure out what we're looking at. So I'm going to draw these correctly. Got to be careful. Yeah, I think I'm okay. Yeah, I'm trying to be careful with the directions that I've made this guy right here, because I can see that I have the potential to have messed this thing up. No, I'm good. So I'm going to draw them down and make sure I use the magnitude. Okay, so here's ones that I know, right? So I know that this is coming down, and I know this is coming to the left, right? So this is my A, B, Y, and here's my A, B, X, right? And then this are these guys up here. So we have our A, so C, X, A, C, Y, right? So I know everything about this one. So I'm going to use that one at both spots. So here's my A, B, X, and my A, B, Y. And I'm just putting this one here because for completeness, that's not actually even necessary. But I've used this one as my reference, so it's getting pinned. And I know already that I'm going counterclockwise. This thing, no, BC is going, yeah, counterclockwise. Yeah, because of this right here. Doesn't really matter, but if I'm going to draw the arrow, I might as well get it right. It's going to have a normal acceleration, and it's this right here. It's going to be orange, so that's 15 degrees. So this is the acceleration of, what is that, C with respect to B in the normal direction. And let's try to get this one right. Right, let's assume, once again, we're doing that guessing thing. That's coming down that way, so that means that arrow looks like this. Here's your 15 degrees. And here's our acceleration of C with respect to B in the tangential direction. Now, sometimes I'll write it out over to the side up here. I guess I'll write it up here. Acceleration of C with respect to B in the normal direction is omega BC squared LBC. We found that to be 1.7256 squared 24. So this comes out to 71.47 inches per second squared. I didn't write this anywhere, but I can try to remember that he's going to be that times the 24 when I go back into there. Okay, so let me write out the equation that we're describing as right up here. We're going to say that AC is equal to a acceleration of C is going to be equal to the acceleration of B plus the acceleration of C with respect to B tangentially, and acceleration of C with respect to B in the normal direction. So in the Y, I'm going to start with the Y direction. And you go Y, because I know this, I know this value from up, I just wrote X and Y. Wow, that was weird. Y and X, there we go. I know this value completely. I just found it up here, right? And I know this value. So that's going to allow me to get what the alpha is going to be. So I'm going to write this out the right way here. Negative 320 that we found from up above is going to be equal to negative right here. So it's a negative 672.8, right? That was what I got right here. And this guy right here is negative as well. So it's a negative alpha BC times 24, and it's going to be the cosine of 15. And then we're going to have negatives, all still y. It's still all these things are negative. Negative 71.47 times the sine of 15. Therefore, alpha BC comes out to a negative 16.02 radians per second squared. So I guessed BC incorrectly. It's actually accelerating clockwise. But we will just go ahead and keep the diagram the way it is, and then when it comes to time to plug in a value, we'll put in the negative for this. So in the x direction, we have a negative, and this AC was alpha CD times 20. It's going to be equal to the B direction right here, which remember was negative 434.6. And now we go to, so that's it took care of that. Now we go to this, and this is also negative, but now it's going to be put in that number, which is negative, right? Because it's actually going the other direction, so that's why that will work out there. Times 24, and then times the sine of 15. And then lastly, we'll see this as a positive x component. So plus 71.47 cosine of 15. And if we do all that, we get an alpha CD of 13.30, and it is positive. So that one we guessed correctly. So now we have the answers that we were seeking. We have omega CD, call it a vector, is going to be up above was 4, right? Is that what we wanted to find out? Yeah, 4 radians per second and counterclockwise. And alpha CD is going to be 13.3 radians per second squared counterclockwise. Kaboom! Hopefully I did it right. I don't know. Could have met lots of opportunities for mistakes. So if I make a mistake, mea culpa. Have a great Easter. It's Good Friday. It's a pretty good Friday.